It's a very early morning here in Jerusalem, and I will talk about computational indeterminacy, which is now a hot topic in philosophy. It is known by different name. I will call it computational indeterminacy, which is a term that was coined by Jack Copeland, who gave a talk on this topic a few days ago. I forgot to share the screen, so here it is. And I will distinguish between two kinds of computational indeterminacy, that has been considered in the literature as a unified phenomenon, and I will try to show that we talk here about two different kinds of computational indeterminacy. I will just start by saying that debate about indeterminacy started 30 years ago when John Searle and Hilary Putnam advanced the ideas that basically every system, every physical system implements every program, algorithm, or automaton, and that led to what people call pan-computationalism, namely that every physical system performs every computation. Back then, people were quick to respond and say that Putnam and Searle simply assumed an overly liberal notion of implementation, and they argued that it takes more than simple homomorphism to implement an automaton. And if we put these constraints, additional constraints, then these indeterminacies or trivialities can be avoided. But people also realize that the indeterminacy of computation is here to stay. And even within additional constraints, some physical systems perform simultaneously more than one computation. And because of it, indeterminacy became a guide to the nature of physical computation, namely to how we individuate computational states, and I will say something about this in a moment. When we talk about computational indeterminacy, so what I said that I want to refer to two kinds of indeterminacies. One kind is what we call functional indeterminacy that concerns a functional or formal characterization of the system's relevant behavior, roughly how its physical states are grouped together and correspond to abstract states. The indeterminacy claim here is that there are several ways of grouping physical states together, such that each grouping can be the computational structure or vehicle of the physical system. On the other hand, the interpretative indeterminacy concerns the manner in which we interpret these abstract states, or briefly, we talk about the formal mathematical or logical content of these states. And the indeterminacy claim here is that there are several ways of assigning formal content to the abstract functional states of the system. Under each assignment, the system computes a different mathematical or logical function. Now, probably you didn't understand a word of what I said, so I will just give an example that will make things much simpler. So let's start with this Tristable physical gate. It has two input channels and one output channel. It maps voltages to voltages according to this table from 0 to 10 volts. And this is what the system is doing in terms of input-output physical function. Now we can abstract from the physical properties and for instance, assign the abstract state A to 7 to 10 volts, B to 4 to 6 volts, C to 0 to 3 volts, something like this. And then what we get is this table. Now we can look at this table and call it the functional organization, as philosophers sometimes do, of the system, the same system P. And in terms of input-output function, that's what the system is doing. It maps sets or functional states to functional states. But then, and here comes the indeterminacy, we can also have coarser-grained groupings of the same physical system P. So for instance, if you look here, we can put under A 7 to 10 volts, but under B 0 to 6 volts. And then what we get is this table. But we can also put under, let's say, A tag 4 to 10 volts, and under B tag 0 to 3 volts. Then we get this table, and you can see that the two tables are not isomorphic because you can look at the output column that you cannot map one to the other. So basically what we have, and now here we have three ways to have functional organization. And if we are talking in terms of implementation, we can see the system is implementing three different automata, or at least input-output functions. So this is what I can call functional indeterminacy. In this case, the physical system P can be seen as having at least, of course, you can have more, three different functional profiles or implementing three different automata. And the indeterminacy claim is that each such profile can be seen, at least potentially, as the computational structure or the vehicle of the system. Now, the philosophers then debate is on whether all these functional profiles are also actual computational profiles, and if not, what is the ingredient that singles out the computational structure? So for instance, David Chalmers thinks that the system basically has all these computational structures. Other people think that it has only one of them, at least in a given context. So some people would say that the true computational structure of the system is only the more basic one. Some of them will go even to the voltages. But most people would say that in a given context, the system has only one computational structure. And then the question is, what is the factor that determines the computational structure of the system? And people usually go to context here. And some people will say that it is the content that matters. This is the semantic view that I hold. And others, mostly mechanists, will say that other factors will affect the computation. Other non-semantic but contextual factors make the difference and single out the computational structure, in this case, for instance, out of the three potential structures. I will not talk much about this. You can read it about this in my forthcoming book on the nature of physical computation. Now, I want to move to the other kind of indeterminacy, which we will call, and by the way, I forgot to say, when I say we, as you saw in the at the beginning, the paper is written by Philippos, Papayannopoulos, Neo Fresco, and myself. And now when we talk about interpreting the function indeterminacy, what we do, we interpret the same functional states. So for instance, let's take one of the tables that I showed before. And now we can assign some mathematical or logical content to the functional states of the system, in this case, A tag and B tag. So here are I will give two possibilities. The one possibility, we interpret or we assign to A tag the truth value true, and to B tag the truth value false, and then we get this table, which is the OR table. And under another assignment, we assign to A tag the truth value false, and to the state B tag the truth value T. We get this table, that is the N table. So in this case, we consider system, the same system, as computing either or and. So this is what we call the interpretive indeterminacy. In this case, the or and difference surfaces we interpret the same, and this is the important thing, the same abstract functional structure in different ways. So the indeterminacy claim is that the system can be seen as computing or and as computing and. And this idea was highlighted in the paper by Fresco, Copeland, and Wolf, and who noticed that we can reinterpret the same functional states, and this results in what they call dual functions, where you simply switch the truth values. Now, in the examples of interpretative indeterminacy that are found in the literature, the range of the interpretation is limited usually to universes that are populated by formal mathematical logical, like the truth values, or other abstract entities such as numbers and sets. And again, the philosophical debate here is on whether the interpretative indeterminacy reflects computational indeterminacy, and if yes, what is the ingredient that singles out the computational structure? And here again, there are philosophers like Dimitri Coelho-Molo and Joe Duers who thinks that the interpretation is irrelevant to computational indeterminacy, and other people who think, like me, who think that we have to find an extra factor that will tell us whether the system computes in a given context or whether it computes in a given context the logical function and. So this is basically the interpretative indeterminacy. So yeah, if I can summarize the difference, now we can see the difference between two kinds of indeterminacy, I think, quite clearly. Let's go back to this slide, which is about functional indeterminacy. So the same physical system we started with, P, we can group the physical states in different ways, such that we get different functional profiles. This profile is the left side profile and the right side profile. Each one of them, potentially at least, can be seen as the computational structure or the computational vehicle of the system, or what some people call functional organization. But now each one of them, we can now assign some mathematical or logical content to the functional states. For instance, here we can assign as to A the truth value true, to B the truth value false, and then we'll get the XOR function. But if we assign the truth value false to A and the truth value true to B, we get the XOR function. And the same we can do now with the right side table. We can assign as we did when we assigned the truth value A true to A tag, we get, and false to B tag, we get the OR function, and when we switch truth values, we get the AND function. So again, the functional indeterminacy arises when we group, and we have different groupings of the same physical states, and interpretative indeterminacy arises when we interpret the same functional states in different ways. For instance, when we assign different truth values to the same functional state. So this, it looks like it's a very simple distinction. So why people didn't notice this so far? And one answer, I think, is that when we give computational descriptions, we don't, we simply bundle together these two ingredients, the functional and the interpretative. So for example, in one of the examples in the literature, let's say that we take now just these two tables, and we assign truth values to them. So we assign to A true and to B false, so we get this XOR, and we assign to A tag true and to B tag false. So now we assign truth values to the different functional tables. So in this case, we see the left side table as we can describe the system as computing XOR, but the right-hand side table, when we use this, we can see the system as computing OR. So this seems to be like on some kind of interpretative indeterminacy, because we are talking about computing different logical functions under different interpretations. But in fact, as you can see, the real indeterminacy here is not interpretative, but functional, because we basically, it arises since we started from, and this we can see here, different groupings of the physical states. This is the real source of indeterminacy, and then we simply assign truth values, but to different functional states. So this is why we got indeterminacy. And when we talk about a computing system, we put together the two kinds of descriptions, the functional and the interpretative, and then we, it seems it's very hard for us then to distinguish between the two. Okay, last point that I want to make is that, and this is, I think this is still tentative, is that we can use this distinction also to differentiate between two kinds of radical computational indeterminacies that we find in the literature. The first one is are the results of Putnam and Searle that are known today as triviality results. And these indeterminacies, we get them when we put no constraints on the groupings of physical states. So when we put no constraints, as we started, and I pointed out this at the beginning of the talk, then the functional indeterminacy really deteriorates to triviality results. So we can have all kinds of groupings and see the system basically as, every system as implementing every possible automaton. So I think that the triviality result is a limiting case of the functional indeterminacy. On the other side, we have another radical indeterminacy in the literature, and this people call deviant encoding. It was pointed out by people like Stuart Shapiro, Michael Rescola, Diane Proudfoot, and Jack Copeland. And in this case, the indeterminacy is that we give to the functional states very different interpretations without putting any constraints on them. In this case, we can get the system as the result that every physical system computes basically every number theoretic function, including even non-computable functions. So in this case might be seen as a limiting or extreme case of interpretative indeterminacy, where no constraints are put on the interpretation function. So I think basically that I'm done. So I want to leave some time for discussion. So as summary, I can say that we characterize and distinguish between two kinds of computational indeterminacy, which has traditionally been regarded as a unified phenomenon. One kind is a functional indeterminacy, which has to do with different groupings of physical properties into different abstract structures. And the other one, the other kind of indeterminacy, has to do with the interpretation of the physical abstract state of the system. So basically, I'm done here. Thank you for attending.
Thank you very much. Thank you, Professor Shagrir, for your very quaint presentation. And we already have one question. Do we have more questions? Okay, so Martin is starting all our conversations now. Please welcome, Martin.
Okay, I have one small comment and one question. The comment is that I can see some kind of confusion in the use of and or by non-native speakers of English. If you go from Narita to Haneda Airport in Tokyo, then you will see informed driver if you see suspicious person and suspicious object, which basically means if you see a bomb but you don't see a suspicious person, don't bother. Yeah, so I use it in my discussion with Japanese students about the use of and or that is confusing. So it could be there is some kind of reflection of the problems within cognition. But my question is, actually, I asked this question Oron several years ago. At this time, there was no clear answer, and I wonder if now there is more clear explanation for this. How it is with NAND? Yeah, is there? Can we see similar indeterminacy when we are talking about NAND gates?
Yes. So. Yeah, so about just the first question, I mean, I agree, and one thing that we can I can say here is that what we show is that, for instance, with or and the end, is that in different contexts the system can be used to compute. I mean, in one context you can see it as computing and in another context you can see it as computing or. This is one of the interesting things about indeterminacy, that it is sensitive to context, and you can change the computational profile or computational structure or computational identity of the system when you change the context. Then I think that now, and maybe Neil, I see is here, he's still drinking coffee, so I let him one maybe minute to recover, but I think that in the case of interpretative indeterminacy, so you can have a dual function of NAND, right? Near or
yes.
among about this.
NAND, and I think it's XOR. It's, XNOR, sorry, XNOR.
And it appears this similar way.
Exactly
Like,
similar, yeah. So basically, out of the 16 2 input, 1 output Boolean functions, you can divide 12 of them in the same way as and or.
I lower my hand.
Okay, please.
And I raise again.
Okay. So, but if this is a direct follow-up, Martin,
No.
Okay.
I'll be waiting for.
So, Rao, welcome. Please pose
Thank
your
you.
question.
I was just wondering, very glad to, see both Jack Copeland and also Oron Shagrir. Thank you very much for this talk. I just have one question essentially related to the comment that Marcin made, the example that he gave very nicely about the suspicious person and suspicious object. Now, if you take that case and how do you interpret these two indeterminacies? Can we sort of apply this to that particular case and explain what is functional indeterminacy and what is interpretative indeterminacy? That might be very interesting to understand in terms of physical terms.
Right. So, so we have to get into of course, the details of the example. So, so for instance, the indeterminacies that I describe is that possible indeterminacies is, for instance, you have you can think about this physical gate P, and you can I already took off the presentation, but you can think about this as, in one context, it is put in auditory context, in another case in visual context. Of course, you can think also about the suspicious and bomb contexts, but but as I see it, for instance, if this is my solution to the indeterminacy problem, that, for instance, if you take this gate and put it, let's say, in a visual context and connect, let's say, one visual context to 0 to 3 volts, and another and 4 to 10 volts to another visual contact or another factor in the environment, then in this case it will be more natural to think that the computational structure has to do with splitting the voltages at 3 and not at 6. But maybe when you move the same physical system into visual content, to auditory context, maybe you will split the voltage at 6, because one auditory content is correlated between 0 to 6 and another between 6 to 10. Now you can think about the same, and of course it depends on the details, with the bomb and suspicious. If 0 to 3 is correlated with bomb stimuli, let's say of bomb, then you will get, now I can forget if it is the end or the or, you can, but you get one of them, and then when you split it at 6, let's say 0 to 6, it is correlated with the suspicious person, then you will choose the other gate. So this is a case, in this case, this is a case for me of functional indeterminacy, but of course you can have the same thing with interpretative indeterminacy, that you have the same split of voltages, but in different contexts. When you correlate it with either bomb or suspicious, in one case you get the and in the other case you get the or. So this is very roughly. Of course, we have to get into the details, but I think if you read, as I said, the paper I mentioned here by Neil Fresco and Jack Copeland and Marty Wolf, or you can read my work, you can see some examples in detail.
Great, thank you very much. That's very clear.
And thank you. We have time for one more question, Gary.
Thank you. Oron, glad to meet you finally. My question is about this. Suppose we interpret logic in terms of colors. So this may be an interesting way. So for example, if you say all F's are G's, we can make that blue, but we combine that with something's an F, we can deduce some F is G. So you combine blue and yellow and you get green. And the same thing, the no F is G could be red. And then when you combine that with the yellow, you get orange, and the orange would be some F is not G. And if you do this, you'll see that if you make it as a traditional square, red and green will be opposites, and blue and orange will be opposites. And if you add the contraries, you'll get purple between the red and the blue, and you'll get there's an interesting way of getting the traditional logical relationships through color mixing. In this case, it's a subtractive view. So let's think of your two ways of getting indeterminacy. It's well known that the visual system just divides the color spectrum in a way because of human beings, the way the rods and cones work, right? And then so there's a way of explaining why human beings will see green as green and blue as blue and so forth. And so I was thinking that one way of trying to resolve the indeterminacy is to use the cognitive system that the human being has. The rods and cones tend to divide.
For some reason, we don't hear you.
Okay.
Yeah, I would say, yes, thank you, Gary, for the proposal. As I said, yeah, there is a hot debate about what is the missing factor here that removes the indeterminacy. And I think your proposal is certainly one option. So I welcome you to join the debate, yes.
Thank you for an interesting paper. You get the same kind of interesting thing, your duality map between, when you get and or and so forth, the logical dualism is related to the inverted spectrum problem.
Okay, yeah, I think, well, I have to get into understand the details better, but it sounds like a very interesting example, yes.
Yeah, the Blanchet hexagon would be something that would work with the propositional logic that you used. Very interesting paper.
Thank you very much. Thank you, Professor Shagrir.